Hey everyone, in this video we're going to be continuing to work with the fundamental theorem of calculus. Specifically we're going to be setting up some problems to evaluate them, but it's going to look a little bit different than the functions that we practiced evaluating last time. Really what I'm trying to do in today's video is set you up for context problems, and then in the next video we're going to be working all in context. Um, yeah, so okay, up first, I just have give the equivalent statement. Here's really what I'm looking for here. And again, this might seem trivial for now, but I think it'll help us when once we get to context problems. So for our first one here, this is an integral from 8 to 3. Okay, if you actually had a function, you would antiderive it, and then you would evaluate the antiderivative at 8 and at 3 and subtract them. Well, let's just say if our function that we're integrating is f, then our antiderivative would be capital F, and I would evaluate this at 8, and I would evaluate this at 3, and I would subtract them. And that's literally all I wanted to do to point this out for you here. I think you'll see why in a couple problems. For our next one, okay, we're starting with f prime. So if I'm anti-deriving, I would just need to get rid of the prime. So my integral would evaluate to regular f of 7 minus regular f of 2. And then let's see, how about, ooh, for this third one, see how I've given you capital F? So that means this is the area of little f, area of little f. So I think this one's one that we're kind of working backwards. This could be replaced by the integral from 1 to 3 of little f of x dx. And I know, so like I told you, if I actually have a function, my favorite way of evaluating is to come up with that function and say like 3 and 8, and then go from there. Again, I think this will help you for problems where we're dealing with net change or where we have physics that we'll look at a little bit in section D and then a lot in next chapter. So, okay, here we go. Suppose little f is that semicircle function. Capital F is the antiderivative of little f. And then if capital F of 5 is 7, find f of negative 5. Well, okay, so remember how we said that like the area functions were always an integral from some starting point? It could be 0, it could be 2, it could be 7 to x to somewhere else. Well, this is the kind of problem where we don't really know where it necessarily starts, but we can use these clues to help us still figure out what we need. So let's say the integral from negative 5 to positive 5 of our function there, 25 minus x squared dx, this would represent the area, um, has to be some other area function capital F, because we said f is the antiderivative of little f, evaluate at the upper limit minus evaluate it at the lower limit. So if we got this actual area here, well, we know this is a semicircle of radius 5. So its area then would be pi, its radius is 5 squared, and then cutting it in half because it's a semicircle. That would have to equal the area function's upper value, which is 7, minus the area function's lower value, which rearrange a little bit, get a little creative here. I guess we'll have to subtract this one over the other side and subtract this one over here, or however else you want to clean it up. Let's see, we'd still have the 7, but then we'd subtract 25 pi over 2. And I know what you're thinking. Again, you're thinking why? Well, my easiest example, which is going to come up in the next section, is going to be like displacement in your physics class. Displacement, it's related to position, but it's a change in position. So that's kind of what we're doing here. Kind of what we're doing here. Okay, one more time. Let's say, okay, so we have f prime, so we have the first derivative of f. We have a specific value for f somewhere. Our job is to find another one. Let's see. So I know the integral of f prime of x from 2 to 8 would have to be represented by regular f of 8 minus regular f of 2. I know this area can be found easily. Oh, I'll actually have to antiderive it here. So maybe I should have written the function out since we're going to antiderive it. 9x squared minus 5. So let's see. Remember the 9 is just a coefficient, so it comes along for the ride. We're going to increase the power by 1 and then divide by the new power to reverse power rule. And then minus 5, and we're just going to add an x there for the constant. We'll evaluate that between 2 and 8. And that will give us the change between this function at 8 and this function at 2. So it's kind of like, in this sense, maybe this will explain a little more. Pretend like f is like a position function, and then the f of 8 minus f of 2. That's kind of like displacement. Again, I know not everyone's taken physics, so I'll explain this more in the next video. But so integrating doesn't actually necessarily move you up from like velocity to position. Integrating just helps you find how much change occurs. So that's what we're looking at here. Now we're using how much change occurs to figure out an initial value. So anyway, let's see. I've kind of run myself out of room here, but 9 over 3 is just 3, so I'm going to simplify that. I'm going to evaluate this left side. So let's see, I'd have 3 times the upper limit cubed minus 5 times the upper limit. That'll be my top half. Minus, now I got to do it again with my bottom half. So 3 times 2 cubed minus 5 times 2. And then that equals f of 8. Oh, f of 8 is the one we don't know. F of 2 we know is 7. I'm sorry, I should have put 7 over here. So that is f of 8 minus 7. So if we can figure out what number all this is, let's see. You want to just calculator that? I mean, 8 cubed, 64 times 8, I don't know. Starting to get pretty big. Let's calculatify it. Let's see. And then here's the other thing I'm going to do is I'm going to take this 7, I'm going to put it over here. So I'm going to do all of this in my calculator, and then I'm going to add 7 to it. And so let's see. Okay, I'm kind of glad we calculatified that. Oh, whoops, that includes the 7. I already added the 7, my bad. So again, officially what we're doing when we're integrating is we're finding how much change occurs. And then like if you know a starting point and you know how much change occurs, you can find an ending point. That's basically what we've done here. I got one more page for you. Let's turn. So this is kind of a classic AP problem here. Well, really, it's a bunch of small AP problems thrown together. So typically, these would kind of be multiple choice questions that would show up. But AP loves to give you tables of information. And so I've given you a couple repeat values or repeat questions here. Like you've seen average rate of change before. I'm just bringing it back so you see it all mixed together in the same context here. So here's what we have. You have a regular function f. I meant to highlight that. You have a regular function f. You have its derivative. You have values of its antiderivative. Our job is to compute a whole bunch of things. So for our first problem, we are going to compute this integral. So integral from 1 to 3 of f of x dx. Well, again, we know, hey, I don't have a function here, but I do happen to know that integrating gives me the value on the antiderivative at 3 subtracted by 1, which, hey, these are things I can get out of the table. I see f3, f1, so 11 minus -1, which would give me 12. Let's see, b is the average value of f over this interval. Remember, the average value of a function is the integral to get the area divided by the width. Because again, area divided by width is going to give you some measure of average height. So let's see. This would then be capital F of 4. Because again, I don't have the function for little f. So let's see. What do we have here? Oh, that line's too long. That doesn't matter. 35 minus 1 over 3. Third. Oh, yeah, because I got to minus -1. There we go. There's my mistake, which gives you 36 over 3, which gives us an average value of 12. I was like, I'm pretty sure I designed this problem so it came out with a whole number. Up next, average rate of change. So let's see. Now it's been a minute since we did rate of change. Remember, rate of change, that's a slope idea. And you see the word average, that means slope between 2 points. So this would be the function, um, the two y values, the change in y divided by the change in x. So this would be the slope of the secant line, something we talked about well, a couple weeks ago now. Actually, it depends on when you're watching this video, I guess. And let's see, so that would give us 11, an average rate of change of 11. And then for our last one here, ooh, we'll have to get a little creative. So really, remember, you can split integrals along addition or subtraction. So this goes from 2 to 4 of f prime of x dx plus the integral from 2 to 4 of 5 dx. Let's put them in pieces. So this piece, well, I know that's going to be go up one level. So instead of f prime, it's going to be f of 4 minus f of 2. And then with this guy, remember there's the property there. You can either anti-derive it. You can say, oh, its antiderivative is 5, evaluate at 2 and 4. Or just the property with constants is, you know, the graph of a constant is always going to be a horizontal line, right? So the area underneath it is always going to be a rectangle with the height of that constant. So you can kind of bypass the antiderivative if you want. And this is one of the properties. You can just say, well, it's going to give me a rectangle of height 5 and width 4 minus 2. So that's pretty chill. Let's see. Go back to my table here. F of 4. Regular F of 4 was 33. And then what else do we need? 2. So 5. So 33 minus 5. 33 minus 5 plus 5 times 2 is 10. Okay, so really 33 plus 5, 38. No big deal. Cool. Like I said, that's what I wanted to talk about today. In the next video, we're going to talk more about this net change idea. We're going to bring a whole bunch of physics into it. Thanks for watching.